In the last video, we defined our random variable x as the number of heads we get after flipping a coin 5 times, and it's a fair coin. And then we figured out the different probabilities that the random variable could take on different values. Let me rewrite them all here. The probability that we get exactly 1 head, or 0 heads, actually, let's start there. The probability we get 0 heads, and that's the same thing as getting 5 tails, we figured out was 1 out of 32. The probability of getting 1 head, we figured out, was 5 over 32. The probability of getting 2 heads, probability that our random variable is equal to 2, what was that? I think it was 10 over 32. Yeah, it was 10 over 32, or 5 over 16. 10 over 32, which is equal to 5 over 16. The probability that we get 3 heads, that was actually equal to the same thing, 10 over 32 is equal to 5 over 16. And that made sense because the probability of getting 3 heads is the same thing as the probability of getting 2 tails. And the probability of getting 2 tails should really be the same thing as getting the probability of getting 2 heads. And then finally, or almost finally, the probability that we get 4 heads, that was equal to 5 over 32. Which also makes sense because the probability of getting 4 heads is the same thing as the probability of getting 1 tail, right? And 1 tail should be the same thing as 1 head, so that's why these numbers are the same. And then finally, the probability that we get all 5 heads, which is the same thing as getting no tails, is 1 over 32, right? The probability of no tails is the same thing as the probability as no heads. So let's draw this. Let's draw our probability distribution. Okay, let me draw the x-axis. That's not thick enough. Let me draw it. Do it a different color. Alright, and just let me draw y-axis. Almost there. Alright, so what are the different values that we care about for our random variable? And notice these are all discrete values. They're all particular finite numbers that we care that our random variable can take on. And that was actually a function of our definition of the random variable, right? This random variable, number of heads after 5 flips, you can't have an infinite number of values here. Your value can either be 0 through 5, right? And it can't be a non-integer even. But the important thing to realize is that there's a finite number of values that this random variable can take on, and that's why we have a discrete probability distribution. Alright, so the probability that it takes on, let me just draw 0, 1, 2, 3, 4, and 5. And this is for our random variable x. So this is the number of heads in 5 trials. And let me draw the high points first. So the first one, let's see, the high points are, oh, they're all right there. See, 10 30 seconds. That's the probability of 2 and 3, and they're the same. Let me draw a little bar graph. So 2 and 3, let's just say that this is 10 30 seconds right there. I'll draw them the highest because those are the highest values. 2 and 3 both hit 10 30 seconds. Actually, let me draw it a little differently. Let me make it so they touch each other. So let's say 2 is there. And then let me draw 3. And 3 is also there. There you go. Alright, what's the probability that you get 1? That was 5 30 seconds, so that's half of these. These two should be the same height. So that's 5 30 seconds, should be like that. And that's the same thing as getting 4 heads, so that's like that. Let's assume that this 4 is down here. And then the probability of getting either 0 or 5 is the same thing. That's 1. So that's 1. It's going to be 1/5 of this height. So it's going to look something like that. It's going to look like something. And let's say this last one is for 5. Nope. The drawing is the hardest part. It's going to look something like that. Alright. And so this is for 5, and this is for 4 right here. And this right here is 10 30 seconds, or 5/16. 10 30 seconds. This is 5 30 seconds. And this right here is 1 30-second. What I have just drawn is a binomial probability distribution. or it's it's a particular instance of the binomial probability distribution. And actually, as you get to kind of an infinite number of values, and once we get to the continuous, this will approach the famous bell curve that you hear about, where things actually start looking like a bell, where it'll start looking like that. And we'll do some, maybe I'll get Excel out and I'll do it where I start saying, instead of saying, the number of heads in 5 trials, if I did this as, the number of heads in 5 million trials, you'd start, these bars would get very, very close together, and you'd start seeing them approach this thing that looks like a bell curve. And this is it's a very important distribution, one, because it actually describes a lot of random processes, but it's actually very important in statistics generally, because a lot of times in statistics you don't know the underlying mechanism that's generating your results, and you just assume that there's just a bunch of random stuff going on, and they just all you just add up a bunch of random events. And when you're adding up random events, that's like counting the number of heads, and then you end up, so you assume that a lot of things have well, in the discrete case, a binomial distribution, and in a few videos from now, I'll show you the continuous case, which is the normal distribution. And this is really important to realize, because sometimes people make that assumption about certain things, and the biggest one, and this has probably the most negative repercussions, especially in this type of financial environment, well, they'll assume that some process has a binomial or a normal distribution where it really doesn't. Right? Because if you assume that something has a distribution like this, you start saying, oh, well, the probabilities at these ends are really low. But what if the distribution is, something like this? And I'll do more work on this. I don't want to get too advanced too fast. But the general idea, it's really important to understand the assumption you're making when someone says, oh, we assume it's a normal distribution, we assume it's a binomial distribution. But with that said, that's a little bit of a nugget of why this is important going into the future. But just to kind of review a little more what we've already studied, let's think about this. Why is this called the binomial distribution? Well, if you think about it, when you flipped 5 coins, or when you had 5 flips of the same coin, each arrangement, I'll pick an arbitrary arrangement of heads and tails, each circumstance of heads and tails, I guess I could call it, that's one of them, 5 flips. Each of these have exactly a 1 in 32 probability. In fact, there's exactly 32 ways I can draw some combination of heads and tails here, right? So each of those have a 1 in 32 probability. And what we essentially did in the last video, when we said, okay, what was the probability of getting exactly 2 heads? We essentially said, okay, how many of these circumstances, or how many of these, I guess we could call it, how many of these permutations had 2 heads? And we counted them up, and we said 10 of them have 2 heads. And that's why the probability was 10 out of 32. And the way we figured that out is, for example, if we said 2 heads, we said, okay, one of 5 flips could be the first head, and then one of 4 flips could be the second head. And then we don't care about order, so we don't care if, flip 1 was the first head and flip 2 was the second head, or it's the other way around, so we divide by 2. And we said that this was the same thing as 5 factorial. Actually, let me do it color-coded. This part is the same thing as 5 factorial over 3 factorial. And then 2, that's actually the same thing as 2 factorial, because 2 factorial is 2 times 1. Right? So in general, let me write this down. The probability that x equaled n, and this is for the x that I defined, the random variable, the number of heads I get in 5 flips of the coin, it was equal to 5 factorial divided by n factorial, right? In this case it was 2. 2 was n. We said was the probability that we get exactly 2 heads, times 5 minus 2 factorial, right? And I encourage you to review, because it really is important to get an intuitive feel of this. I encourage you to review the videos I made in the probability playlist on binomial coefficients and on this flipping of coins type of probability problems, because I go a little more detail in the actual intuition of this. But if you watch those, or if you have a little bit of experience with this, you would recognize that this is the binomial coefficient. And I actually even have a video why it's called the binomial, because these coefficients show up when you actually multiply binomials. Binomials are just things like, if I just have x plus y and I start multiplying it by itself, take it to different powers, the coefficients of these tend to be, well, they are the same as these. And I give you a whole video on why that, well, that's why that works. And so this is why it's even called the binomial coefficient, and why this is called the binomial distribution. But another way of writing this, a shorthand, is 5 choose n. And they say that because what were we doing? We said we had 5 flips, and we were choosing 2 of the flips to be heads. Or in this case, we have 5 flips, and we're choosing n of the flips to be heads. So this will tell you how many of the different permutations satisfy our condition. And then we say, well, what's the probability of each of those? It's times 1 out of 32. So this is why it's called a binomial distribution. Each of the values, the probabilities for each of the random variable values, there you can figure them out by using your binomial coefficients. Anyway, I just realized I'm out of time again, and don't worry, I'm going to do a couple more examples with this because I really want you to get the hang of the binomial distribution before we move into the normal distribution. See you soon.